So, hello everyone. Today, our team is going to present a simple but quite effective way of doing this project. So, since we have a visitor here, I'd like to first introduce this project. So, the task is to try to build a classifier or a model to distinguish fake documents from real documents. So by fake documents, we mean the documents generated by a trigram model. So that's it. So since our method is so simple, I find, in fact, this is the most difficult slide for me because I cannot pronounce my friend's name quite well. So I'm gonna let them introduce themselves.
I'm Kenton.
I'm KP. I'm Ashik.
And I'm Xinlei Chen. Yes. So before we move on, we'll first summarize a few methods proposed by other teams, since we have already presented other teams' work on it. So a way to do it is first we extract semantic features of any kind, like semantic features, like named entity recognition features, like syntactic features, maybe POS tags, or maybe the most effective feature is unknown feature, the unknown word, because for the generated documents, it can be unknown words. There can be unknown words. But for the true documents, it can be any words but unknown word. But after browsing the data, we find some guys, or maybe the TAs, have viciously hide the out of vocabulary words and replace them with unknown words. So we cannot use this simple technique to tell which one is true and which one.
People tried it 5 years ago.
Yes. Okay. Yeah. Anyway, that's a kind of feature, but that's a failure. So after we have these features, we build any kind of classifier on it, like SVM or logistic regression, or maybe we try to combine different weak classifiers like AdaBoost or simple majority voting. But our task is, our goal is to keep it short and simple, because let's think about it. It's a quite nice way to push forward the boundary of state-of-the-art method. But what we have done is, as Ronnie has mentioned, people have done it 5 years ago. It is not a state-of-the-art anymore. So instead, we can just find some state-of-the-art language models, and without any feature crafting or anything, we want to find out which one. We want the state-of-the-art models to act like true documents, true document generators, and the trigram model as fake document generators. So what we did is we built 16 top-perform language models, n-gram models, with various smoothing methods like Kneser-Ney smoothing, Witten-Bell smoothing, and we just use a simple linear combination of the output of the language models. So given a new sentence, since we have two kinds of models, one is the model given by the assignment, the trigram model. The other is any of the model we have built from the 100 million data set. And given a sentence, we estimate the log likelihood, or the likelihood of this model generates this sentence. And we simply compute the posterior because there's a uniform prior on it. And for documents, we just sum over or product over the likelihood of each sentence. That's very simple. And we use a 3-language model toolkit, and because it supports different smoothing method. And so after doing this, we found out our model is a generative model instead of models built by others, like discriminative models. But it is generally accepted that generative model won't work well for tasks or competitions. However, we have noticed that since the fake documents are generated by trigram models, and we already know the generative sources of these fake documents, so we believe that this generative method should work because we do not need the effort to build models to model the probabilities of the underlying data probability. So that's it. Sorry.
No worries. Cool. So I'm going to talk a little bit about our results. As you mentioned, we used the SRI language modeling toolkit, and we were able to get a 95% accuracy on the dev set. And what we used with the SRI is we looked at 6 different discount methods, and from 4 grams up to 9 grams, because we know that it was trained on a 3-gram model. So with each of these, they have a back off also. So like if you have a 9-gram that's too sparse, it'll back off to the 8-gram and stuff. And we looked at and saw which ones were the best performing on the training set. So you'll see like some of these had some pretty good performance. And it wasn't always necessarily like what you'd expect, like good Turing. The lower ordered ones performed a little bit better, like the 4 and 5 grams as opposed to the higher ones. So we had a combination of 36 of these total, and we decided that we were going to combine them using just a soft weighting scheme. So we just took the top 16 performing on the training set, and we combined them. We looked at just treating them all equally, and same for the unseen documents, saying each one of them contributes equally. Or what we ended up doing eventually was taking the score that it had on the training set and using that as a weight and then normalizing it so that everything summed to 1. And then we were able to get like an overall thing that looked at a bunch of different models. We also looked at using some other things like combining in other features like parse speech tagging, SVMs, and really trying to do some more deeper analysis and separate this data. But it always just decreased our results. So we figured we were just overfitting. And in some ways it makes sense because like the SVM and stuff would be very good at picking out which model was good on some certain sub cases that could have been very good in the training set, but just overly optimized on that. So this weighting scheme, though kind of simple, just should prevent overfitting. But like I said, we only had 95% accuracy, so we were kind of curious to see what we were missing. So there's 10 test cases that we were missing on the dev set. And we decided, like, what's the possibility? So what's the upper limit? So we actually did a survey of 60 people and asked the 10 questions of whether or not they were generated by human or machine. And unfortunately, people got 8 of them right. So I guess our internal language models are still better than anything we were able to build. So there's still some room to go. But we can look at the 2 that didn't do. So some of the issues you get were something like let's take, which is too short. Like when you have like a trigram model like that, I don't know. I wouldn't know which one that came from. Or in the other one, this one kind of talks about some of the issues you run into with language. So you'll have all these unknowns, a letter, but it's also transcribed broadcast news. And you look at it, it says as a 911 operator as opposed to 911 operator, so there's some issues there. And we also did the survey to a variety of people in geographic locations outside the US. So, do you have a question?
Can we take a vote here? What people think about this? Did
Sure.
you disclose already whether this is
No.
real?
No.
Okay. Who thinks it's real?
Which one?
The lone one.
I think it's real.
Okay. Who thinks it's real? Who thinks it's fake? I don't see the hands going up very high.
Because you include a lot of unknown words. I don't think that's actually a fair comparison.
Well, makes it hard. Okay. What's the real label?
So the real level of let's take is it's false, and the real level of 911 operator is true.
Okay.
Cool. So, but yeah, you see some of the cultural things. We had this out all variety of geographic locations. So like people wouldn't even know what 911 was in some of the places we did the survey. So a lot of interesting things. Some of the other stuff we did is we tried, like I said, some SVM with the features, logistic regression, add a boost, boosting all these things, but we just would overfit horribly. And we could get really good results, but then they would, we were thinking it was overfitting. We also looked at recursive neural nets and a few other things. But yeah, I guess that's the time or so. Any questions?
Yeah. I wasn't really clear, so what was exactly the feature that you used? So you talked about a lot, but you used just one?
Oh, no, we used 16 of the SRI ones, which we combined.
Yeah, but those are models, so what are the features get scores out of these?
Oh, what is it?
It's just a combination of the output of the 16 models.
Yes, what is the output? What is the output?
It's the problem.
It's a probability. Yes.
So it's
Probability
a
of being
threshold
fake
on the
or
score or what? The
no,
rate?
it's not a threshold. It's just a soft score.
But is it the posterior? You're
Yeah, it's a
calculating the likelihood
posterior.
according
It's a
to one?
posterior. Yes.
Okay.
Yeah.
And it's the likelihood according to one of these models versus?
One of those models with the baseline trigonometry.
Okay.
Yeah. And we just single combination.
So yeah, so in the end there was a big debate. I mean, what to turn in for the final submission, because we had like few 95%, 93% accuracies, and in the end we decided to submit the simplest thing. I mean, the most simple.
Yeah, and so if we can look at the development set, like 10-hour parameters, we can achieve the 99.5 accuracy, in fact. But we we do not want to overfit this model, so we just submit the models using this simple technique.
Does our guest have a question?
No, I'm good. I have a question. I wasn't entirely clear, how did you combine these various models? I mean, you said
Yeah.
in combination, but how did you do the weights?
Okay.
of the development set?
So if you want to.
So if you have like 16 models, and we test each of these models on the training set, and we have an accuracy for each of these models. So whatever the accuracy of a model is, that's the weight of that model. And then we normalize everything to 1. So assume that someone's accuracy is 0.9, so the weight for that model would be 0.9, someone has accuracy 0.99, weight would be 0.9, and everything would be normalized to 1. So it just indicates how good they did in the training set.
Yes, and in fact we have tried to
we tried
raise the
power.
power. We tried a range of 0 to 39. It consistently performs 95% accuracy on the development set. And yeah, if it is raised to the power of 40, then it's 94.5%. And we think our model is quite robust. That's it.
Thank you.
Here is our team, Leo, Dee, Hector, and Joe. Since most of their approaches and methods were already presented, we'll try to keep it really short and focus only on things that are different from previous teams. So we actually have the same approach as many other teams. We train discriminative classifiers, separate classifiers for one classifier and logistic regression to produce posterior. We have the same main hypothesis. We actually have very similar features. The only difference that from other teams, I don't know, maybe nobody mentioned that, when we built Ngram models, we actually set a cutoff value because we thought it might, overfit. So high order Ngram values, I think they should have been included only if they occur like thrice. Otherwise, we discarded them. And that's really the difference, the way how we generated the additional training and dev set. So there was a clever idea mentioned by another team. So they split the training set into smaller documents, but it took a different approach. We actually generated a larger set. Well, to this end, we needed actually to hack the CMU toolkit a little bit because it doesn't generate from the model provided. And the newer toolkit, which can generate, it actually doesn't read the model, neither in the text nor in the binary form. So we really focused more on preventing overfitting and getting a second dev set, which was 10x the size of the original one. The same machine learning methods. So experimental results are also similar to other teams, like the best results we're getting 0.92 accuracy on the dev set, and regarding the soft metric, I actually think we're doing worse. And this is our insight. the perplexity value is plotted for 3 grams and 4 grams models. This is an interesting picture in our opinion because this is for the training set, for the original training set. Here you can see that they are linearly separable, and that's actually perfectly can be done, almost perfectly. And we believe that there is a latent variable that defines the complexity of the lexicon. So if you kind of fix this variable, well, what it means is that the complexity of the lexicon can be, like the lexicon can be hard, a lot of rare words. Then perplexity will be high with respect to kind of all models. And you cannot use only 4-gram or 5-gram model to distinguish between data points. But if you combine them, you can separate them perfectly. There were other features that we used that actually achieved better separation, like average portion of repeated words. It's almost like, also separates almost perfectly, but in reality, when we combine all of them, it didn't work well then perplexity is computed from the 3-gram and 4-gram models. That's our last slide. We also did error analysis. So so this is the graph of accuracy versus the number of sentences. And as you can see, we are doing quite well if the sentence is long, but if the sentence is short, it's not so good. And one problem with other features, with all other features that we tried, so they work similar to n-grams, they work only for long sentences. But for short sentences, there is a high variance and none of the additional features actually worked well. So that's it, and thank you very much. Questions are welcome.
So did you use, so that, I really like the plot you had of a trigram model and a quadgram model, and you looked at the perplexity of both and then plotted the quadgram perplexity on the y-axis. Can you go back a couple slides of that one? It's like
Sure.
this one. Mm-hmm. So did you use this as a feature? Did you use like a ratio of 4-gram to trigram?
So we include both, so we two-dimensional features, trigram and 4-gram.
Okay.
Yeah, that's separate one already.
So the model includes only perplexity for 3 grams and 4 grams, the final model. But I also tried a bunch of different features, including in the syntactic parsing score. But they actually kind of perform kind of well, like 0.88, 0.9 in the depth set, but not as good as the n-grams. And we can see because we have a larger depth set, we kind of see that, okay, this is not overfitting, because for the other depth set, we're getting also 0.92, I guess. So it's probably doing well.
What was the accuracy if you used only these 2 features?
We only use only these 2 features. I think the other team actually the other day mentioned that they also took 3-gram and maybe 5-gram, and they also got 0.92. So that's
These points to the development set?
This is a training set. For the development set are fuzzy clouds that you cannot separate them.
Right, that would be very interesting to see. You know, this is remarkable. But it would be very interesting to see what happens in the development.
So there, for the lower perplexity for 3-gram and the 4-gram, so there are some overlapping, and we believe it is a large variance for short documents and the perplexity produced.
Regarding the variance, there was also another unique feature, which was kind of counterintuitive, because there was a team that argued that balanced set is better. Well, it's probably better for some models, but it wasn't better for n-gram models. So what we actually did when we generated data, we increased the size of the document that we used for training, because in our opinion that kind of makes so these clouds are making them like kind of narrower, so the direction of larger variance becomes more clear to the model, and it learns the kind of mean values of perplexity better. So we added some insane number of words, like 2,000 words per sentence, or per document, so it was like plus 10 sentences or something. And it actually performed a little bit better, but it definitely didn't perform worse. And we can be sure because we used 2 depth sets, so.
Did you show the final results?
Oh, yeah. It's not final, it is depth.
Well,
So it's 0.92 essentially.
What's short versus complete? Short sentences?
Oh, no, no, no. As I said, we had a lot of features and a lot of Ngram models.
Short model.
It's just 2 Ngram models perplexities. That's it.
The simpler one was. Is that what you submitted?
Yeah. Well, I think that actually it's not clear which one was. I mean they were comparable. The other one maybe it was point. And you never know. It may be overfitting.
And in the software trick, you're reporting 2 to the soft, but it looks like it's actually.
No, it's pretty low. It's actually lower than other teams.
Right, but I think maybe the constant factor is off. The perplexity should not be less than 1.
It's 2 to the power of posterior, or to the log posterior. So it cannot be, so as it is the closer to 1, the better. It's the average probability of guessing correct label. Geometric mean, of course.
Okay, yeah, 1 over that would be perplexity. Okay,
Yeah. So.
all right, thank you.
Hello, everybody. My name is Malcolm Greaves, and my project partners are Shilpa Balaji, Lars Mahler, and Lawrence Wang. And we are going to present our solution to the authentic text classification problem that we're all so familiar with. So in this presentation, I'm going to discuss the processes and approaches that we undertook to solve our problem, including a review of our infrastructure that we made to make our problem a little bit easier to work with, and a lot of interesting features that we came up with, our model selection process, and the results of our final model. So, as everyone knows in this project, the really interesting part of it comes from the feature engineering. That's what separates, the very great solutions from the okay solutions. And early on, critically, we thought that it was a very important part of our solution to be able to quickly iterate on features. We wanted to be able to work in parallel, to have people come up with features and then combine them together with existing features we had and evaluate their effect on the model. So this figure up here shows the training and classification pipelines in a schematic overview of our problem. The lowercase letters are not all uppercase, rather indicate programs. So Featureize is a program that we use to convert the articles into an article or a matrix of articles described by features, where the ith j entry in the feature is the feature value, the jth feature function computing a value for the ith document. And so this infrastructure allowed us to have rapid iteration because we were able to simply run the Featureizer program again if we had different features and produce a new matrix and train many different models on the same matrix. We also introduced a part into the program where if in case of a feature function failed to compute a value for a certain document, it would fall back on a value that was the average value that it had on the training set. So next, Lawrence is going to talk about some of our features.
So given that some number of groups already talked about topic modeling, we're not going to cover this. Something I don't think any other group has covered yet is, so we try to look at the difference between the distribution of words in an article compared to the expected value or the expected or number of times each word would appear. And so I'm going to assume that you guys aren't very familiar with the chi-square test for goodness of fit, so I'll just introduce it briefly. Basically, what it does is it measures how closely the outcomes in some distribution are to the actual expected values. So, for example, if you roll a die 1,200 times, you expect the numbers to be for each roll to be close to 200. Of course, you wouldn't expect it to be actually very perfect. Like the first row there would be fake data, but in that case, the difference between the outcomes and the expected values are very close. So the test statistic will be very small. In a real actual simulation, since I didn't actually roll a die 1,200 times, the numbers will be a little further away from 200, but still relatively close, and this will lead to a somewhat larger value for the statistic. And in a biased case, it will have a really large test statistic. And so the intuition behind using this is that for a trigram-generated data set, the expected value should be or the actual outcomes for counts of different words should be very close to the expected value, or relatively close. So we should have a relatively small chi-squared test statistic. Whereas for real data, because when somebody speaks or talks about a certain topic, they'll choose to use certain words more than others, we'll have a higher test statistic. And this works okay, but it's really more powerful when the articles are very long. If you have a 5-sentence article, it's harder for this to work out.
Okay, so the next feature or set of features that we developed was based on some initial analysis of the parse trees of the real and fake sentences. These are sort of extreme examples, but what we noted was that in some cases the real sentences had nicer, more balanced parse trees, whereas the fake parse trees in some cases tended to be right branching just due to the wandering nature of the sentence that was generated. So these are a little skewed. It wasn't quite this clear cut. There were examples of both in both categories. But we hypothesized that on average, a parser might have more difficulty making sense out of a fake sentence. And there might be differences that a classifier could pick up on. So we computed, we parsed each sentence and computed count statistics and conditional probabilities of the different productions within each tree. The next topic, or the next feature, was motivated by the class language models paper, where they talked about semantic stickiness. And so I think other teams have talked about this. I won't talk about it too much, but we essentially calculated the mutual information between word pairs in sentences. And the thought here was that in a real article, you're going to have more coherence, and you should see a higher score here than in a fake article.
So another feature that we considered was the burstiness of the language, which is something we've talked about in class a couple times. We chose to focus on, in particular, the burstiness of nouns and verbs because those are generally the more semantically informative parts of speech. So the way we measured this, I guess, was we looked at all the words that were labeled as nouns or verbs, and then whether, if a word that was labeled as a noun or verb occurred multiple times within the same article, then we considered that bursty with respect to either nouns or verbs. This feature actually tended to perform kind of well. Our classifier did rely on it. Another measure that we used was the cosine similarity between sentences as well as between different parts of a single sentence. So the motivation behind this feature was, as we were looking through the real articles, we saw that when people are talking, when they're conversing with each other on these broadcast news transcripts, there's a lot of echoing that we see. So someone will be like, I think this about like this topic, and the next person will be like, oh, well, I think this about this topic. And so there's a lot of parallelism between consecutive sentences, or that was the hypothesis at least. And so the pairwise element of this was we looked at consecutive sentences and took the pairwise cosine similarity of those sentences representing each sentence as a word vector, and we averaged across all pairs of sentences, and that gave us that feature. But we realized that this kind of wasn't doing so well on the smaller articles because smaller articles are much harder, and also there's not really a pairwise element that you can compute. So what we did there was we split each sentence into two, and then we measured the cosine similarity between those two halves of the sentences. And that's what this plot is actually. So this cosine similarity is on the x, and the article length is on the y, and you can see how it performs differently based on the article length. So yeah, it really only ends up working better for the longer articles, as you can see.
So we trained a logistic regression on all the features, and we did L1 penalization to prevent us from overfitting. And the numbers are around 85 to 86. We actually sort of penalized ourselves a little because when we generate so we took the training set data that was provided and we broke down them into smaller sections, and we actually biased it towards smaller articles because we assumed that that would help us do a little better on the smaller articles. And so this is the curve of how well we do based on the length of the article. That's it.
Yep. Questions?
I think you have the most unusual features. That's very nice. Very, very nice.
That's very bad. Okay. Thank you.
Lala and myself, I'm Fatima, and we had the same problem, article classification. And I'll just discuss the approach very briefly and then go over our features, which are very similar to other teams' features, and then discuss the results and lessons we've learned. So we started with an initial set of features that were basically linguistically motivated. We tried to featureize natural language, and we also tried to look at patterns in the fake articles. So we tried to do things that are, we tried to go in two different lines when coming up with the features, featureizing natural language and featureizing language found in the fake articles. And then we tried to independently compute these features and then filter these features and eliminate those features that were very computationally expensive or not very informative. Then finally, we combined these features into a model. And according to the informativeness of the model trying different sets of features, we again refined or eliminated additional features and ended up with an improved model. So we didn't do a feature selection like the rigorous feature selection, but we did kind of try different combinations of features and finalize the classifier with the most informative ones. Okay, so the features we had are very similar to features already discussed. So we had a ratio of the perplexity of 3 grams to 4 grams. So it's actually, there's a mistake in the slide, it's the other order. And as you can see, there is a clear difference between the behavior in real and fake articles. The ratio is higher in real articles, and there is almost no overlapping between the two. So this feature was very informative. And then we looked at type token patterns and differences between fake and real articles. And as you can see, again, there is a difference between the behavior in real and fake articles. So this feature, when actually we tried to build a classifier using this feature alone, and it gave us an accuracy of 88%, given that the article length is at least 200 tokens, which is still short. It didn't do very well with extremely short articles, but if the article has at least 10 sentences or 200 tokens, it would still give us a reasonable accuracy. We used one syntactic feature, which is the number of sentences without any verb. And we expected that this number would be higher in fake articles, and it was. We tried other syntactic features, but it was hard to compute, and it was hard to train the parsers, and it ended up being not a very useful feature, so we didn't include it in our final classifier. This graph does not have titles for the X and Y axes, but it was an attempt to model burstiness, and it was, burstiness was defined as the number of matches found in the real or fake articles to a list of n-grams computed from the real B and C corpus. So we expected that the number of matches would be higher in the case of real articles and would be lower on average in the case of fake articles. The original graph was not very clear, so we had to do some transformation. Jeffrey, I believe this is in log scale for the average number of matches. Okay, so the takeaway from this is that there is a different distribution. But again, it was not very useful on the dev data when we tried it. We also thought about the deviation in sentence length. We also noticed that the fake articles had sentences of various lengths, and the real articles had pretty much the same distribution. We thought it's a matter of style, and so we thought that this would be a useful feature. Another feature we used was a semantic feature, which is the content pair matches. I believe this was explained, so I'm not going to go over that in details. But we used another similar feature, which is the matches to stop words or function words. So the intuition here is that the rare features would be relatively, or rare events would be relatively biased high in the real articles, and the common events would be relatively biased high in the, rare events would be relatively biased high in real articles, and common events would be relatively biased high in the fake articles. So we tried Maxent at the beginning. It didn't give us very good results, and we ended up using SVM. The results we had on a combination of lexical, semantic features were 91%. All combined gave us 88%. There is a mistake here. And the other features were not very informative. So we ended up, we decided to submit the classifier based on this combination of features. Here you can see an error rate analysis. As the article length increased, the error rate went down. We thought, as a way of improving the accuracy of the classifier, to do training set balancing, but we didn't have time to do that. And now that we heard that it gives 95% or more accuracy, we're not sure if that was leading to some overfitting. We thought about doing a structured feature selection. We didn't do that, but we tried different combinations of features and not every possible pair of feature. We thought about experimenting with more models. We have the intuition that some features would work best with a linear classifier and others would work best with other types of classifier, and to focus on features for classifying the short articles. So a few lessons that we've learned from this. Sometimes you do have the linguistic insight, and it's clear that the real and fake articles behave differently, but it was not always easy to capture that using a statistical measure. So that was part of the challenge. The other thing we noticed is that even when you don't have a lot of linguistic insight, the data can tell you a lot. So we noticed, like many other teams, that the statistical features or the n-gram, the empirical features, were very informative. So with those features alone and without including the semantic features and the syntactic features, you would still get high accuracy, around 90%. So we didn't have to go far beyond trigrams to get high accuracy. What a trigram can tell you, a 4-gram can tell you, and so on, for this specific task. Of course, for other tasks in NLP, you would need to do more than that. Okay, any questions?
I have a question about the graphs you made. So, were they produced using some kind of smoothing or spline interpolation? Yeah, all graphs. So I see a lot of those smooth curves.
No, some of them are scatter plots and some of them are line graphs, but we removed the point. It was generated using Excel, and the data points we generated from the feed.
Okay, so it's like those very smooth curves.
Yes.
Yeah. So are they really just you have a lot of those points, or just a few points and you connected them?
Yes. Yes. Yes.
Okay, so I would advise that in this case you just connect the points with straight segments.
Right.
This was kind of confusing.
Yeah, I know, but then I don't know. I couldn't change the size of those points. They were overlapping because they were big. So I thought the pattern would be easier to see using something smooth.
Okay.
I have a question. Well, actually, that was regarding this graph. Is it really a clear separation here, or is it just was unfortunately that red is brighter than blue and comes over it?
So this is, you can think about these as the number of matches found in the real articles or fake articles to a list of n-grams computed from the BNC corpus. And the intuition that the number of matches would be higher in the case of real articles. And as...
Well, yeah, I understand this. I'm trying to understand if it's actually, you see a clear separation here, or is it just like two fuzzy clouds that are all overlap and we just don't see the overlap?
You're not seeing the overlap. There is an overlap.
Yeah.
So this maybe is like above the threshold, you can be sure it's blue, but below the
Right.
threshold, you don't know.
Right. So there is some overlap here, that's right, but you can't see it. But there is also a pattern of separation.
You had another graph that was showing the count of birds, I think it was.
The count of?
Was it the count? Oh, count of sentences that
Yes.
you have verbs, right.
Mhm.
So did you just take the straight count, or did you normalize for the number of sentences?
No,
in the
straight count. Normalize over the number of the sentences? Yeah. It's like for each article, we consider the number of sentences.
I think that would to eliminate bias towards long articles.
Can you go to the error analysis by length? Document length? It seems like everybody found that, right? That the shorter it is, it's very easy to get the very long ones, and it's reasonably easy to get these, and then it gets really worse. I think it's nice to have this curve, and the next step might be to focus on, like, separate into two efforts. One, focus on very short sentences, which might require, they may not be separable, but they might require different thinking than the longer ones. One comment I had is that when you use the type token curve ratio, this is very, very similar in essence to the chi-square measure that Lawrence used. Because if you think about chi-square as capturing the number of times that words repeat, every time a word repeats, that's a case where the number of tokens grows, but the number of types doesn't grow. So it's sort of a single statistic as opposed to the multiple statistics you can have for each individual words, which you combine later. But they're both after the same thing. To what extent, the word choice is rich or limited. Finally, a question. You suspected that very frequent words are biased one way and very rare words are biased the other way.
Yes.
I wonder what made you think that. A priori, I wouldn't expect that an n-gram would be biased with regard to unigram frequencies. It might be. I'm not saying it's not, but I'm saying that a priori I would think that an n-gram, a trigram, would be good at capturing marginals like unigram distributions and bigram distributions and trigram distributions perhaps, but not 4-gram or 5-gram or 6-gram, because it sees the world through a second-order Markov chain.
Right. I think we did find like an evidence of that bias when we created the list of content words and compared the matches found in real and fake articles. But I think Jeffrey and Selene would be able to answer that question in more detail.
Yeah, when we analyzed the real and fake articles, we found out that fake articles have more stop words. So we assumed that because the trigram model creates the sentences based on the trigram probabilities, that's why fake articles have more stop words in it. So that's the reason why, behind our feature. So we basically counted how many stop words, the probability of seeing a stop word in an article, in real and fake articles, and also we did an analysis of the frequent 4-grams, like how many, probability of seeing a 4-gram in an article and in a real or fake article.
So it may be that in real articles, these stop words are rarer. It's not that in fake articles they are higher than normal.
I'm glad you did it. I'm glad you found empirically that that's the case. It is true that that's the case, but it's because of deficiencies in the trigram model. The trigram model does not optimize unigram. If you have done it on the unigram model, you wouldn't have found this difference. So I think we can test your hypothesis, and I think it would fail. I think it is because the trigram is optimized for something else, and it does not try to be consistent on unigrams.
Yeah, we can test that.
Thank you.
Just the point that you mentioned about this error analysis, we actually at the beginning we tried to focus on the short articles and the long articles because we saw that our features are very good at long articles, but on the short ones they are not. So we tried to go for parsing the sentences. We thought that if we can find whether these sentences are grammatical, like if you give us one sentence article, then if it's grammatical or not, it might be the best solution to get whether it's a fake or a real one. So we tried the parser, but the parser we've been trying didn't have any statistic to show us log probabilities of these things. So we couldn't actually actually add that feature to our features that we have.
Thank you.
Hello everyone, this is our team. I'm Karthik. He's Jonathan Barker. Sujay Jauhar and Pallavi Baljakar, and we are tackling the same problem. So basically, the features which we use can be divided into 5 classes. The first class is the basic features, which are just simple counts of, like, we count number of verbs, number of nouns, or number of stop words and everything. And the second feature, the second class of features we focus upon are grammatical features, because we found that the fake articles are badly framed grammatically. So we use 2 kinds of parsers. One is constituency-based parser and the dependency-based parsers, and we actually exploit the bad parsers given out by both these parsers. Now, the next class of features can be is semantic coherence features, which try to judge whether a sentence, even if framed grammatically properly, makes sense or not. Then we focus on topical coherence, which look at document-wide features and try to judge whether a document pertains to a smaller set of topics or it just jumps from topic to topic. And then we have signal-based features where we treat each word as an impulse train, and we sort of do some dimension analysis using standard signal processing techniques. So, as I described earlier, the basic features are just the counts, and more features would be explained by Jonathan.
So to go into more depth on our grammaticality features, the first one was the part-of-speech language model perplexity. We did this by training a 5-gram part-of-speech model over the 100 million word corpus. The next few were derived from the dependency parser. The average length of verbal modifiers we thought would be important, because we noticed that the trigram model tends to string a bunch of modifiers together, and you'd expect the average length of verbal modifiers to be longer in the fake sentences than in actual sentences. Also, we looked at the ratio of sentences with verb heads or not, because in a grammatical sentence, you would expect the verb to be the head of the dependency parse. We also looked at the average number of subtrees containing verbal heads. And then dyskinetic modifiers was also based on the dependency parsers. You'd expect that the trigram model to have a lot of modifiers which don't correctly attach to a phrase. And then simple things like the absence of nouns and verbs in a sentence, and the fluctuation of length across sentences. The last 3 were statistics taken from the Berkeley parser, which are just the average parse confidence of all the sentences, normalized by sentence length, because as sentences get longer, even if they are grammatical, they're going to be less likely. And the log likelihood of the parse tree given the sentence, and the average log likelihood of the sentence. And now I'm going to talk about the semantic or topical coherence features. So one of the things we looked at was the repeat ratio of content words. So you would expect that topically coherent articles would have a greater ratio of repeated content words to non-repeated content words. We looked at the average semantic similarity of content words. This was done by looking at the average pairwise semantic similarity based on the distributional vectors of content word types in the document. This was done using the Sena parser. We also trained an LDA model over 200 topics and looked at the maximally prominent topic. You'd expect that real articles would have a higher score for the most prominent topic. And then we also extended some of the prior features like the semantic similarity of content words onto a sentence level and inter-sentence level. Now Pallavi's going to talk about our signal-based features.
Since the whole point of the whole project was to have fun with it, we thought we'd try something crazy, because initially what people have done is they've considered speech as text and got good results, so we thought we'd do the reverse, consider the text stream as numbers and convert it to a signal and try some signal processing stuff on it. So our whole motivation behind this was, so we basically worked off the POS data stream, and the whole motivation here was, say, if there is natural text, then the way a thought process would work generally would you think of the nouns, the verbs, and adjectives, and then the rest would be like fillers around it. And a trigram model may not have some structure within it, so we wanted to see if there is some underlying structure, difference in structure between the normal text and the fake text, and if we could get this underlying structure. So 2 ways we went about this. So now our main aim here was to see if there is a difference in the sequence of certain POS tags or a group of POS tags, and to see if there is a difference in the structure of POS tags, as in nouns follow verbs, follow adjectives, so on and so forth. So 2 things we did. So to see whether there is a difference in the sequence, we treated it as a point process. So considering only certain POS tags or a single POS tag, made it into an impulse train where gave ones to the POS tags of interest. So now once you have an impulse train, then calculated the pulse number distribution, which is basically, so if you consider each document to be a signal of impulses, you frame it, and in each frame you count the number of impulses. So there's a pulse number distribution, and so I get an average pulse count for each frame and average it over all the frames of that document. And the pulse interval distribution is similar, where you calculate the difference between the 2 impulses. But these features are not very good. They had almost an overlap, except the normal documents had a greater variance. But accuracy with just simple thresholding was just around 60%, which was not really great. Then the next 2 features I converted to a number stream. So basically I weighted the different POS tags differently. So I mean, I didn't use any empirical weighting for this. I just intuitively thought that I gave sentence boundary the maximum weight, nouns lesser weight, so on and so forth, till like foreign words are given very less weight. So now since I had a number stream, so this was to find the structure within the document. So for the power spectral density, basically what I did was I framed the signal, and initially from the training, 500 training documents, the real documents, I got an average frame representing the real document, and I cross-correlated that real frame with every single frame in the test set, and after cross-correlating it, I took the FFT, the Fourier transform of that, and I get the power spectral density. So I take the first PSD0, the first power spectral component, which supposedly represents the real power of the document. And actually this kind of gave actually good results. I mean, it was not very great, but it gave around 70%, which I think was good considering the features. And then the final one was the fractal dimension of the document. So basically here what we did here, the basic aim was to see whether there is some kind of long range correlation in the real document which won't be there in the fake document. So what we did was for every frame you calculate the range. So now since it's a number stream, you take the cumulative deviation in a frame and you calculate the R by S. So where R is the range in that is the maximum deviation minus the minimum deviation divided by the average deviation. So you calculate that at different scales, and once you calculate that at different scales, you plot a graph, and the slope of that graph gives you the Hurst exponent. So basically what the Hurst exponent gives you is, since it's a slope, it will be between 0 and 1. So the lesser the slope, that means there is more. So basically the Hurst exponent is actually used to calculate the smoothness of a curve. So that means there is a lot of deviation, so there is no real structure within the document. So greater the Hurst exponent, there is more structure in the document. So and the fractal dimension was calculated from the Hurst exponent as 2 minus h. But basically from all of these, the power spectral density was a little promising, but then finally we didn't go ahead and use any of these.
So
you bet you had seen more creative features before this, right? Okay, the model essentially replicates what a lot of people have done. We have a feature matrix and just train a classifier on that. We experimented with a number of classifiers, and SVM seemed to perform the worst. What we did to basically tackle the different document lengths was to train 3 different classifiers and basically replicate the training set 3 times and train 3 different classifiers in this process. Our results are sort of okay. On very short sentences, of course, we don't perform that well. We get an F measure of 0.775, and as we get longer articles, we start to do better and better. And overall, we get an average F measure and accuracy of 88%. In an analysis of accuracy versus document length, you see that, again, you don't do really well on the very, very short articles. But by the time you come to a document of 4 or 5 sentences, you're already doing at about 90%, which is sort of nice to see. Finally, we did some sort of feature analysis to see which ones were doing better on what document lengths, and we see that some features tend to do better across all models, and these are the repeat ratio of content words, the part of speech perplexity, and the average content similarity. You can see these. You see as the document length starts to get longer and longer, the semantic features tend to play a more prominent role in deciding whether documents are fake or not. And this sort of conforms to the intuition that longer documents provide greater evidence for semantic coherence. That's about it, and we'll be happy to take any questions. Should I hand it back to Pallavi, because I'm pretty sure the questions are all going to be directed towards.
I'm really happy. I mean, this is by far the most creative. Absolutely. And you got 60% or something there.
But then 50 is a fluke anyway. I mean, so
50 is a fluke, but I don't know.
Yeah, but 70 is certainly remarkable.
Did you try a random feature to see what that would do?
No. Yeah,
just as a sanity check.
So the problem with the one which was giving 70% accuracy was it was taking a lot of time to compute. So it was computationally expensive. That's why we decided to drop that feature. But it was a good feature, actually.
I think it's really creative.
Yeah. So let me ask you. So how did you turn that into a signal? Like for the first 2, I guess for each POS tag,
or a group of
it
POS
was 0 or 1 for each word.
Yeah.
And for calculating the power spectral density,
yeah.
it was you convert each different POS tag into a number?
Yes, a group of POS tags. So I took all the nouns, like the nouns and the pronouns, and grouped them as one number. So nouns, verbs, adjectives.
Okay, so what does that number represent?
The importance of what I thought was important language.
Okay, so it's like for nouns and verbs.
Yeah, nouns, verbs, adjectives, adverbs, and then
So the prepositions will have those scores. Okay.
Just an idea of how to expand it further. Don't go to parts of speech, stay with words. Convert each word to the log probability computed by the standard trigram. So now you converted the text into a stream of numbers. And do any of your analysis on the stream of numbers. I suspect that there may be some pattern there. In fact, let me tell you what I think the pattern is. I think the real world will be more surprising than text generated by a trigram. Text generated by a trigram follows a trigram by definition. The real world follows the trigram up to a point and gets more surprises. So my hypothesis, and I'm cheating because I have done that, is that the real language is more surprising to a trigram model than trigram generated data is to a trigram model. Surprising is when you focus on the extreme cases. So they're more extreme. If you convert words to the log probs, then you have surprises sticking out.
How did you measure the length of in like the parse tree features? How did you measure the length of like a verb? I forgot the term.
The modifier?
Yeah, the verb modifier.
Yeah,
so it was like this
we did a depth first search, and a typical good sentence technically has verb at its head, and it can have another verb in its subtree, basically. So say he killed someone who was doing something. So doing would be in the subtree of killed. So basically we just took the length of killed first, like killed has two modifiers, one on left, one on right, and then we took the length of the doing modifier with one on left and one on right, and we sort of averaged the modifier lengths across.
So would that be a length of 1 for each of them, or a total length of 2?
There'll be two lengths. There'll be two modifiers, so two different lengths.
So if you had a very ungrammatical sentence that had like a very maybe a run-on structure, and you had some verb, and then you'd have a child of that verb, and that child of another child, and that child of another child, and then you would have a verb that would be a length of 3.
Yeah, exactly. So what happens here is like if I have several children of like a single verb, then first of all I have many modifiers, and I can build and what we observed was we actually for fake sentences we had a huge modifier chain length. So our basic hypothesis was like a trigram model is sort of greedy, as in like it tries to like when it's short, but when it's long, it tries to just link on modifiers onto itself. So our hypothesis, so one of our features was just the modifier length, and the other feature was in a dependency parse, all your modifiers still form a good chain. Like if it's a noun phrase of say the last king of Scotland, the last king of Scotland would nicely form a chain among its chain within itself. But in trigram, these things do not form a chain. So a noun phrase like the last king of Scotland would each form its own modifier without a chain. So there won't be any explicit relation between the modified constituents. So these were some of the bad parse feature we exploited.
All right. On this happy note, are we done? All right. Thank you. I really like the cosine measure, it was cool. I like I really learned from every time we do that. We haven't done this one in a while, so we might do it again in a couple of years. It's very nice. It's the kind of project that you can do open-ended. You can work on it for a year. So here's one really nice relationship between this problem and the real-world problem. Not like I just not real word, but CAPTCHAs. You know the problem of determining whether someone is a person or a machine. So the most common kind of CAPTCHAs are visual CAPTCHAs, where they distort some picture or distort some word, and you have to type it. This is actually not that hard to break. The kind of CAPTCHA we've been working on was language-based CAPTCHA, when you give people a sentence and they have to decide whether it is fake or real. We worked on it seriously for a while. There are a couple problems with it. One is that they can just randomly guess. It's only one bit of information, and if they get it wrong, they try again. So it's not, you need something with a higher branch out. But you can create things for higher branch out, like give them a whole document and ask them to identify the one sentence that doesn't make sense in there. But anyway, what I really want to point out, even in the simple problem of fake versus real, the inability of machines or models to do what people do means that there is some imperfection of the model. In fact, what you guys all did was try to find the ways in which the trigram model is an imperfect model of reality. Try to focus in on that difference. So there's a nice loop between the existence of CAPTCHAs and the closing of open problems in language and generally in AI. You can create a formal system that shows as long as there's an open problem in AI, there will be a CAPTCHA, and vice versa. The day we solve all the problems in AI, there won't be any CAPTCHAs by definition. And as long as there is a CAPTCHA that you can show is still a CAPTCHA, that means we didn't solve all the problems. So you can exploit one for the other. Anyway, I really enjoyed it. I enjoyed the presentations. I enjoyed the analysis. I enjoyed standing and talking to you guys. Oh, don't forget the FCs, please. They're very useful. Please, good, bad, or indifferent, fill the FCs. I think I mentioned I do read all the comments. I do like, what I like the most is if everybody participated. That would be awesome. And it's anonymous, so it could be as blunt and
So what about the results? Did you finish running the tests, or who gets the trouble?
Right. Oh, we don't know yet. So the poor VAs are going to be working day and night to get the results running. They're going to affect the truffles a lot more than they're going to affect the grade. So I didn't tell them that yet, but the effect on the grade is going to be the minority of the grade. The majority is just using some techniques, coming up with creative ideas, using what I mentioned before, using linguistic intuition, using some statistical methodology, whether you happen to fall on the right. The truth is that the things that perform the best are pretty mundane, ho-hum, trigram, foregram ratios, right? Several people discovered that. So it's the real world. In the real world, the most exciting things don't always work the best. But it doesn't matter. I wanted people to try wild things. I'm really happy that people took me seriously.
And we can invite them to come up with, more intelligent models to generate fake articles to use for future projects.
Yes, absolutely. Maybe take the power spectrum and sample. No, I think it's a great idea. Really great idea. Glad you did it. All right. Thank you. Thanks very much. We'll see you at the party.